Swayam Prabha. Digital India. Educated India.
Welcome back to Mechanics and Control of Robotic Manipulator. Last few classes we have seen basically robot dynamics, mainly we call manipulator dynamics. So you know, like manipulator dynamics again divide into two. One is we call motion dynamics, the other one is what you call structural dynamics. So we have seen more focused on motion dynamics. So we have seen what way we can actually like formulate this. So there are two formulation method, or you can say derivation methods we have seen. So in this particular class, once you derive the equation, we can write it in certain form. That is what we are calling equation of motion in state space form. So that is what we are actually like trying to see. In this case, if you look at it, that equation of motion can be written in the general space we call configuration space, which is what the manipulator space, or we can write it the tool, or you can say end effector space, which we call operational space or task space. So in the sense, the equation of motion can be written in state space form, either in joint space or task space. In this particular lecture, we are going to see both in detail. So in that sense, what we are actually like rewriting this equation what we derived in the last few classes, where tau is the actual like causes of, or you can say causes, and where this q dot and q double dot are the motion. So we have a relation between, you can say, input and you can say output. Here output is motion and input is actually like your input forces, or you can say joint forces and torque. So in that sense, the general model can be written in a nonlinear form as a simple function. Okay, but this can be actually like made it for, you can say, numerical integration point of view, or in the other way around, you can say for a forward dynamics point of view, we can rewrite this equation in this manner. In the sense, for us, you can say simplification, or for the integration part, you know q double dot, then you can integrate double times. What you will get? You will get the q. If you integrate single time, so you will get what you call q dot, right? So in the sense, these are the two states variable. This you can obtain by integrating in that. So in that sense, you need to have a separation of q double dot. So that separation will come. So in that sense, you can see one side without having any acceleration term. So other side you have a acceleration term alone, but in that acceleration term alone, we are actually like taking n cross 1 as a vector. Now the coefficient of this n cross 1 vector in this tau equation would give a coefficient matrix. This coefficient matrix what we are going to call as a inertia matrix. So we will see in detail what are the property of this inertia matrix, but this is the simplification, or you can say simple model for numerical integration. In that sense, what you have input and you have actually like output in acceleration and other form. So even some people even further actually like you can say make it detail, where you can see that the gravity they separate it. So we have separated already the initial term. So now we can actually like separate the gravity term. Then you can see whatever left, that we can call as other effect. So that other effect I put it in a capital V as the vector. So now in that sense, you can see this is the little detail model. Even you know like this other vector would be having further component as a centripetal and Coriolis component, and even you bring the friction. But right now we are not bothering about friction, because if you you can say remember the derivation which we derived, which is actually like based on rigid body. So based on rigid body, we have seen that there are only kinetic and potential energy we have taken in Lagrangian Euler, and even in the what you call Newton Euler also we have seen acceleration, then inertial forces only, right? So in the sense, the dissipative, or you can say conservative forces we have not seen. So in that sense, the frictional term directly will not be coming. So we will see how the other terms can be divided. So in that sense, what one can see, the equation of motion can be further, you can say, detail it, where you can see that the V of q comma q dot further divided into two different terms. So one is we call actually like Coriolis effects. So the other one is actually like centripetal effect, where this would be come with you can say vector. So now this B of Q is actually like a rectangular matrix, but the C of Q is actually like you can see it is a square matrix. So what is the dimension of Q dot? That would be actually like, for example, you have, so Q you can say I to something, for example, I say theta 1, theta 2, theta 3 are the 3 variable. So now theta 1 dot, theta 2 dot, then theta 2 dot, theta 3 dot, and theta 3 dot and theta 1 dot are the 3 combination it can come, which will generate the what you call Coriolis effect. In that sense, this is the you call a vector. This would be having n into n minus 1 divided by 2, okay, cross 1. This is the, you can say, size of this particular vector. In that sense, this would be B of Q would be n cross n into n minus 1, sorry, yeah, whole divided by 2. So this would be the size. So now you got idea what is actually like the Coriolis effect. Coriolis effect would be happening due to combination of linear and angular velocity, so of that particular link, right? That way we can actually like generate. And similarly you can see the you call radial or centripetal effects, that would actually like give you can say something specific matrix. The C of Q would be giving something called as Q symmetricity matrix, in the sense S transpose equal to minus of S, or S plus S transpose equal to 0. So this way it will come. We will see these all detail in later. Similarly, M of Q, which is the inertial term cannot be negative, right? And in that sense, what you can see, M of Q can be positive definite matrix. Further, this M of Q will give one additional aspect, that what we call symmetric matrix. In the sense, M transpose of Q is actually like this, okay. So this all we would be seeing in detail in upcoming, you can say, slides. So now this is the detailed model. It is a more detailed model where gravity term separated, inertial term separated. Further, the V of Q comma Q dot we have further divided into 2 sub terms. Further, if you want, actually like you can make it friction, we can bring it. But right now we will rewrite the equation which we derived in both, you can say, Newton-Euler and Lagrangian-Euler method. So these are the 2 equations which we derived for a 2R serial manipulator, which we call tau 1 and tau 2. So now you can see that the theta 1 double dot, theta 2 double dot, you actually like separate it. Similarly, in the second equation also you separate it. So what that will come? So you are actually like interested this way, right? So you are actually like rewriting this equation, then you will get a coefficient. This coefficient matrix what you call M of Q, which is actually like inertia matrix, right? And further you can see, I already told, once you derived you have to match the units. So you can see like this is giving theta 1 dot and theta 2 dot, this will give the Coriolis component, and you can see theta 2 dot squared, this is giving the centripetal component. The same way you can see here. So here you can see the centripetal term alone is there, because the second body is not getting the Coriolis effect. That is very clear, because the second body is freely rotating, and you can see the other term is actually like the gravity terms. So now we will actually like rewrite in the what you call this form, more detailed form. We can actually like rewrite that. So in that sense you can see that the M of Q will come in this. So now after seeing this matrix, so L1 and L2 are actually like geometrical variable, and as per the criteria L1 is positive or equal to 0. So L2 also positive or equal to 0, and mass cannot be 0, right? If you have a link, that cannot be 0, in the sense M1 greater than 0 and M2 also greater than 0, and you substitute these all. So what one can see, this matrix is actually like definitely going to be a positive definite, that we will see in the numerical simulation side. And further you can see this term is actually like matching with this term, in the sense even you take a transpose, it is giving the same matrix, right? So that is what we have actually like seen, M transpose of Q equal to M of Q, in the sense it is a symmetric matrix. Further this is going to give a positive definiteness, right? So that is what we have actually like seen as a inertia matrix. Let us move to the second term, we call actually like centripetal effects. So if you recall from this, the centripetal term is here is, so minus M2 L1 L2 S2 theta 2 dot squared. So in the second term it is actually like, so m2 L1 L2 S2, so theta 1 dot squared, right. So these are the two terms, right. So now if we rewrite that in a matrix form, where you can write C of, you can write theta into theta 1 dot squared and theta 2 dot squared. So what that matrix look like? This look like this, right. You just to multiply, you can see that related to tau 1, so the C of q comma q dot squared is giving the terms, so minus m2 L1 L2 S2, so theta 2 dot squared, okay. This is m2 L1 L2 S2 theta 1 dot squared. So this is matching with your previous derivation, right. But by looking this matrix, what one can see, the diagonal is 0. This is matching with the skew symmetric, the first criteria, and off diagonal matrix is actually just, you can say, transpose of that, you can see, or conjugate term. So you can see like this is minus m2 L1 L2 S2, but here you can see. So in the sense, if you take a transpose of C of q, okay, so this would be minus of C of q, right. That is what matching, in the sense this is a skew symmetric matrix. You have seen that, right. So now we will go the next one. So this is not having any specific property, but what you can see that the Coriolis effect can be written in this form. So as I already said, n into n minus 1 whole divided by 2 is the size of the vector. So now this matrix is n into n of n minus 1 whole divided by 2. Here n is 2. So 2 cross, so 2 into 1. So in the sense, this is actually like 2 cross 1. In the sense, 2 row and 1 column. And similarly, the other one is n to n minus 1 by 2 cross 1. So in the sense, it is 1 cross 1. So this is what we have actually like seen as the Coriolis effect. So if you actually like take a product, so you can see that the first term would be minus 2 m2 L1 L2 S2 theta 1 dot theta 2 dot, the second term is 0. That is what actually like coming into this also, you can see. So only the tau 1 is having a Coriolis effect and tau 2 is having 0. So that is what we are also getting in this, you can say, effect, right. So now coming to the last one, what is the last one? The gravity effect. The gravity effect, you want G can be brought in out, or you can keep it G, but this is the two terms which we obtain in tau 1 and tau 2. So now this is the gravity vector, and you can actually like substitute G is actually like minus 9.81 or plus 9.81 based on what direction you derived your equation of motion, okay. So this is the basic idea about what you call the equation of motion in configuration space. So let us move further. So you can see, if you want to include the non-rigid body effect, so here what we are calling non-rigid body effect is the friction. The friction would be usually having three frictions. So we usually consider viscous, Coulomb and static friction, but we assume that the static, or you can say kinematic friction, is not important. So then the static only Coulomb is coming, and viscous is actually like a dynamic is coming. In this sense, you can write this tau friction term as additional two other terms. Even these two additional terms can brought into a coefficient and the further quality, in the sense, so you can say state space vector. So this viscous friction is actually like what? So the tau viscous friction directly proportional to the velocity. So in the sense, if the proportionality constant you bring it, that proportionality constant I brought as a B, okay. So the Coulomb friction is similar, the tau, this is I called viscous, the Coulomb friction directly proportional to the sine of the q dot, okay. So then you can actually like see this is what coming. So now the Coulomb friction coefficient also we brought in. So now this is the frictional term. If you rewrite that in a matrix or vector form, I am writing as a capital F as the frictional effect. So that would be written as q comma q dot, okay. So in fact, this q is not really necessary, but sometime you may actually like look the friction is happening somewhere else. For example, you have actually like the joint is here, but there is a friction is happening because of some other term. Then you have to bring that q. So that's why we have actually like generalized the frictional effect f of q comma q dot. Okay. So now based on these all, if you rewrite the more detailed model, the frictional term is added. Okay. Now these all are rigid body effect and this is non-rigid body effect. So now if you assume that this is actually like moving in a space or it is actually like an aerial case and all, then even you can add the non-rigid body effect as actually like you can say aerodynamic effect, then you can actually like add that. Okay, if this manipulator is actually like moving inside the, you can say submersible water or some other fluid, then you will get a buoyancy force that you can add. Okay, but right now it is actually like ground based normal serial manipulator. We can actually like assume these all rigid body effect and this is the non-rigid body effect. Okay, so now this is what we have seen, that equation of motion in joint space. Why we say joint space? So q we call joint space state vector. So q dot is actually like the velocity of joint space vector and q double dot is acceleration of joint space vector, right? So in the sense this equation of motion is written in the form of, you can say joint space or you can say configuration space. That is what you can say the equation of motion here. So now we are actually like talking about equation of motion in operational space. So for that what we can actually like see, so what are the relations we know? We know mu dot as j of q into q dot. So that equation I can take. Further what I know, the tau I can write as j of q transpose into f. So this we have derived, right? So these two equations we are going to use it. Okay. So this is the differential kinematic equation, that too like forward differential kinematic equation. Then if I differentiate further, I will get mu double dot in this form. So from there I can actually like take, so q double dot as, you can write j of q inverse into mu double dot. Okay. So minus j dot q into q dot is coming as q double dot. So what we derived in the previous equation? So in the previous equation we derived a q double dot. We can substitute that into mu double dot term. Okay. Further what we know, so the q dot I can again write as, so j of q inverse into mu dot. So now only one consideration is there, the mod or you can say determinant of this should be non-zero. Okay. Further, if it is actually like j of q is a square matrix, we are actually like fine. If it is non-square, then you have to take j, you can say pseudo inverse. So that we have already seen in the differential kinematics, right? So now this equation we have, and this equation we already know from the statics. So now we can actually like use this again. So tau I can substitute this, and q double dot I can substitute in terms of mu double dot and mu dot. Okay. So that is what we are actually taking this equation and going to substitute in this form. I am not going to take more detailed equation, I am taking a very simple equation which is easy for me to derive. Okay. So in the sense I have written the q double dot in the form of mu double dot. Even here I bring it q dot as j of q inverse into mu dot. Then you can see that the q double dot is in the form of mu double dot and mu dot. Okay. So right now I don't want, but I want write it in mu double dot form. So in that sense I can write this equation in this. So and I know this, but what I wanted mu double dot function of this as f. If I want to write this, so I can actually like multiply and bring all the terms. So then you can see like this is what all coming into a picture. So now I actually like make it separation. So my m of mu is actually like these three terms together. Okay. And n of mu is actually like this term multiply with this. Okay. And this term all together. You can see that is what we have derived. So now you can see like the equation of motion we can write it even in the task space. Now this f would be the end effector forces and moment. So we call fx, fy, fz and nx, ny and nz. Okay. So this is what you call the f vector. So in the sense at the end what is the effect that I know, I can actually like propagate the model and then do it. Okay. So this is the whole idea. So now what we have come across in this particular lecture, we have seen, so what is the equation of motion Okay, that equation of motion can be written in two different spaces. One is actually like the operational space, that is what we have derived here, but more convenient is actually like configurational, or you call joint space. So that is what we derived in the equation of motion, then we can actually like rewrite in more detailed form. So in that sense, so this particular lecture is giving a initial push, so how we can actually like go for in real cases. So based on this, you can actually like give your f or tau, and then you can see your system simulation, and then you can actually design your entire system. So before going to see that in detail, let me show how to derive the equation of motion either in Newton-Euler or Lagrangian-Euler through the help of MATLAB. Then we will move to this form and make it as a numerical simulation in after this, you can say, demonstration in MATLAB. Okay. So the next class would be talking about how to derive the equation of motion for given example in MATLAB. That is what we are going to see. So I hope this is actually like useful. We will see in next class with MATLAB simulation. Okay. Thank you. See you then. Bye.